I think I have a lab next week.
Probably. Is there a reason not to?
No, because we haven't done. I know we had a reason yesterday, and then last week we didn't do one. I forget the reason.
For fun.
Oh, okay.
Yeah. All right, so. We last left off. We have not gotten into orbital motion yet. I think that was the other class. We did centripetal motion. What was the last thing we did?
We did where we essentially took the ramp and
Okay.
changed it.
All right. So there's a bunch of problems similar to what we've done already. So let's add new content. We've so far dealt with objects accelerating because of change in speed. Conceptually, we've dealt with the fact that you can accelerate by other means. But let's do the other means now more with a math background to it. So, okay, what are the three accelerators in a car?
The steering wheel.
Yes?
Gas and the brake.
Yeah. So let's deal with the steering wheel aspect. If I'm traveling at a constant speed, I can still accelerate because I can change direction. If I change direction, I change velocity. Side note, velocity has a direction. So what I'm going to do is I'm going to imagine I have an object traveling at a constant speed around a circle. And those are supposed to be straight. And I'm going to label this angle phi right there. And it's traveling at some speed v. And since the speed is constant, v. And what I wanted us to do is calculate the acceleration. So, what's acceleration?
The change in velocity over time.
All right. And change in velocity, how would you find that?
The initial velocity, the final velocity minus the initial velocity.
Okay. So all you have to do is figure out what the velocities are and just plug and chug, right? So if I'm going to subtract these two, this is my final velocity here, and this is my initial velocity here. I need to somehow be able to add these, or actually subtract them, or add the negative. And it's probably simplest, at least in my head, if we break it down into horizontal and vertical components. So if I'm going to do that, I need to figure out what is that angle right there. And because of symmetry, whatever angle that is, it's the same angle there, despite the way I do it. What is that angle? 12.
Don't think we have enough information
All right, so let's get more information. All right, so I'm going to redraw that triangle. So I got, if I just extend that all the way across, that's this triangle right here. Meanwhile, I've got this velocity here that's perpendicular to the path. So I've got another triangle. That's the angle right there I'm trying to find. I'm just going to label this alpha. That's a right angle. That's a right angle. There we go. What about now?
Well, now we have some more information. One angle is 90 degrees.
Actually, there are three angles that are 90 degrees. That one, and that one.
But that's okay. I see what you're saying, yeah.
All right, first, you wanna keep going? You wanna roll? Somebody else wanna chime in?
I just have a question. How does the bottom triangle have two right angles and then have a third angle? Where am I?
How does it have,
And where am I reading that wrong? Or the first right angle is for both triangles or the top triangle?
this one right here?
The other one.
This one right here? That's this angle right here. That angle and that angle are the same.
Okay.
So we have the larger triangle, which
Isn't there?
has a vertex up here,
Okay.
and then the smaller triangle, which is here.
Yes.
Is that the answer? Okay. All right, so if phi is 20 degrees, what is this angle right here?
20 degrees?
20 degrees.
Isn't that what you just said?
You said 30.
Said 20.
Oh, you said 20.
Oh, and I thought I had that here. All right, so let's draw that bigger triangle there. Hopefully better than that. That's the bigger triangle, the one that goes here.
Oh, you said if that's 20.
If that's 20 degrees, what is this angle here?
70
How'd you get that?
plus 90 plus 20 is 110, 180 minus 110,
And why 180?
because that's the sum of the angles of the triangle.
Sure, we'll go with that. Actually, in Euclidean geometry, yes, when you start getting into warp space, not so much, but that's well beyond the scope of the course. Yeah, 180 degrees. So if this angle here is phi, what would this angle be?
5'7". Not even close.
You said phi 7?
5'7" to indicate that's 5'20", 5'2", that's 5'7".
All right. If this angle here is phi, what would this one be?
Theta.
I'm looking for something in terms of phi.
5.
Okay, phi prime is what I've generally labeled it in the past. What is phi prime equal to in terms of phi?
90 minus, well, I mean, if it's always a right triangle,
Yes, it is.
it would be 90 minus 5.
With a question mark?
Yes.
Is she right?
Yes.
That the question mark in there?
Nope, not the question mark. Exclamation mark.
Factorial?
Factorial.
If that's phi, the angles of a triangle add up to 180 degrees. We are assuming flat space. This is classical mechanics, that's the way it is. They have to add up to 180 degrees. Well, I know 90 is it's a right triangle, so 90 is taken up by that. So these two have to add up to 90 degrees. And so phi plus this equals 90, or this is 90 degrees minus phi. Let's take a dramatic pause for questions.
So I could say 5 plus phi equals 90. Would that be
Phi plus phi prime.
Okay, if I was gonna use prime, it'd be 5 plus 5. 90.
And therefore, if we subtract that from both sides,
Privacy.
other questions? All right. So this angle here that angle there, is 90 degrees minus 5. Now let's look at the small brown triangle here, or with green dashes. That's 90 degrees. What is this angle right here? What does alpha equal in terms of phi?
You said the top angle is 70? Because we just found it over there.
Well, if this were 20, that would be 70.
Okay. And we're just using that for now. We're just using that for now.
Yeah, just as a specific case. So if this is 20,
That would be 70.
this would be 70 degrees.
Alright.
And this would be,
This would be, 90 minus. Wait,
Would it
angle also be 90 minus 5?
so that's 90 minus 5, that's 90 minus 5, and this is 90.
that don't add up.
Euclid would be very sad. We're looking at this triangle right here. Going this way, that's a right angle, that way. That's this triangle right here. That's 90 degrees. This is 90 degrees minus 5. I'm asking about this angle here.
That's just fine.
Would it be 20 degrees?
If this were 70, that would be 20 degrees. Or, in general, 5. This angle here and this angle here are the same. So this, if that angle there is 5, this angle here is 5. Justin, did you have a follow-up? You looked like,
No, I get it now.
okay.
So if we have the angle, if we're given that angle, the bottom one, yeah, I guess, yeah, that'd be what I was thinking. Yeah, so if we have that angle, we also have that angle.
Yes.
And this is just rule.
Well, assuming that this is perpendicular to the radius here.
Okay.
So let's actually test that for a moment. What do I have around here that I can throw?
Oh, I didn't even ask that question.
I'm gonna step to the other room. I'm going to grab a prop and I will be right back. I'm just gonna let it run. All right. Well, I'm glad that fell off before I started slinging it around. First year I was here, we were doing the experiment with centripetal motion and we were slinging this thing around. I hadn't found the rubber stoppers yet. So we're using some of the metal slotted masses with a hole in it, sling it around, and the string broke. So this piece of metal goes flying across the room, goes smacking into the board. No one was hurt, thank goodness. I was doing this demonstration when I was teaching middle school. I will say, I came closer to hitting Scott than I intended, but I did not hit Scott when I threw this thing across the room. But that was first period, and by fourth period, the student comes in and said, Dr. Fox, I heard you hit Scott this morning. No, I did not hit Scott. All right, so as I sling this thing around, the question is, when I let go, which way is it gonna go?
I have no idea.
Well, it depends on where I release it. So if I release it when it's directly between me and the board, which way is it gonna go? All right, so we've got a finger pointing that way, got that way, up,
No,
oh, back.
yeah.
So that way, well, let's. The board, me swinging this thing around. I'm gonna release it when it is here. All right, so we have a, so think of this in terms of a circle, that'd be 12 o'clock, 9 o'clock, or think of it in terms of a clock, 6, 3, and then we have, if somebody says it's gonna go shooting, I guess if we looked at the wingspan, no, that's a bad way of looking at it. Never mind that part. So there's the vote for it's, if I release it here, it's gonna go back here. Is that what you said?
Yes.
And you were the same, or do you think it's gonna be more over here?
Saying like, yeah, more to the left.
More over here?
Yeah.
And Justin, you're saying over here? I'm swinging around like that.
I think it's gonna go directly into the board.
I think, like between like 9 or 10, if you're looking at the clock.
Like 9 or 10, so
Say,
it's gonna go over here. Anyone else want to chime in? All right, place your bets.
and duck.
All right, I am going to face it because otherwise I won't know the point I will release it. I want to release it when it's here. All right. 1, 2, 3. The rest. Why? Why did you go that way?
Because after you let go, it kept spinning a little bit and then went that way. Like it kept moving this way in the, I guess.
It seemed like it would have then hit the door frame or something. All right, so let's talk about inertia. What is inertia?
Something with Newton. You said something about it.
I know there's something called the law of inertia which gets attributed to him, but I really don't know if he actually used the word inertia or not. He might have.
Yes. If something has motion, it will stay in motion.
That's the one that's a part of it.
Is there like the laziness or something?
Ali, see?
The laziness of the object?
I think more of stubbornness than laziness. The reason why it's not laziness is the example that I think in one of the videos is if you're digging a latrine ditch, then if you're lazy, you want to stop as soon as possible. And that is not what it's about. It's you want to keep doing whatever you're doing.
Okay, fair enough.
So,
It's gonna be the best stretch ever.
yeah, pretty much. If inertia, if the latrine ditch or hole was apt, you would just keep digging and digging and digging. Like the diggingest dog. No books of familiarity with that one, okay? So, objects want to keep doing whatever they're doing. They want to keep traveling in the same velocity. Basically, they want velocity to be constant. If velocity is not constant, if velocity is not constant, what has to be in play here? vaguely worded, but, sorry?
Outside force.
Okay, we'll go that route. Yeah, things will keep doing whatever they're doing unless something causes it to change. So, what I was initially thinking of was there's acceleration that I was going to connect to force. So if the change in velocity is not zero, then acceleration is not zero. And if acceleration is not zero, then the total force is not zero. So if one of these is not true, the other two are not true. So when I swing it into the circle, what forces are acting on it?
Your hand.
I do not have Jedi powers.
The string.
I was not touching it.
Oh.
Well, the string. I don't know if there was tension.
There would
There
be
was.
tension. There was tension when I was swinging it around. Tension. So if I did from a sort of a side view, there was tension. There was tension acting this way. It wasn't perfectly. The string was not like this. The string sags on.
Gravity going for weight.
Thank you. Anything else?
Photon. Oh wait, we have a normal force, no?
From
Oh, we're just looking at the ball, so.
what was stopper?
Yeah.
Yeah, it's the tension. Now, if you want to get into the pickiness of what's causing the tension, then you can get that far, but tension's fine. There's no Jedi powers, nothing magical there. Normal force. What about friction?
No.
That was a no? Okay. Alright, so that's it. Those are the only forces acting on it. When I let go of the string, this goes away. So what is the only force acting on it?
Wait.
So as soon as I let go, the only force acting